On the 14th of August, 1894, an excited crowd gathered outside Oxford's Natural History Museum. This huge Gothic building was hosting the annual meeting of the British Association for the Advancement of Science. Over 2,000 tickets had been sold in advance, and the museum was already packed, waiting for the next talk to be given by Professor Oliver Lodge. His name might not be familiar to us now, but his discoveries should have made him as famous as some of the other great electrical pioneers of history. People like Benjamin Franklin, Alessandro Volta, or even the great Michael Faraday. Quite unwittingly, he would set in motion a series of events that would revolutionize the Victorian world of brass and telegraph wire. This lecture would mark the birth of the modern electrical world, a world dominated by silicon and mass wireless communication. In this program, we discover how electricity connected the world together through broadcasting and computer networks, and how we finally learnt to unravel and exploit electricity at an atomic level. After centuries of man's experiments with electricity, a new age of real understanding was now dawning. These tubes are not plugged in to any power source, but they still light up. It's electricity's invisible effect, an effect not just confined to the wires it flows through. In the middle of the 19th century, a great theory was proposed to explain how this could be. The theory says that surrounding any electric charge, and there's a lot of electricity flowing above my head, is a force field. These fluorescent tubes are lit purely because they're under the influence of the force field from the power cables above. The theory that a flow of electricity could in some way create an invisible force field was originally proposed by Michael Faraday, but it would take a brilliant young Scotsman called James Clerk Maxwell who would prove Faraday correct, and not through experimentation, but through mathematics. This was all a far cry from the typical 19th century way of understanding how the world works, which was essentially to see it as a physical machine. Before Maxwell, scientists had often built strange machines or devised wondrous experiments to create and measure electricity. But Maxwell was different. He was interested in the numbers, and his new theory not only revealed electricity's invisible force field, but how it could be manipulated. It would prove to be one of the most important scientific discoveries of all time.
Maxwell was a mathematician, and a great one, and he saw electricity and magnetism in an entirely new way. He expressed it all in terms of very compact mathematical equations. And the most important thing is that in Maxwell's equations is an understanding of electricity and magnetism as something linked and as something that can occur in waves.
Maxwell's calculations showed how these fields could be disturbed, rather like touching the surface of water with your finger. Changing the direction of the electric current would create a ripple or wave through these electric and magnetic fields. And constantly changing the direction of the flow of the current forwards and backwards, like an alternating current, would produce a whole series of waves. Waves that would carry energy. Maxwell's maths was telling him that changing electric currents would be constantly sending out great waves of energy into their surroundings, waves that would carry on forever unless something absorbed them. Maxwell's maths was so advanced and complicated that only a handful of people understood it at the time. And although his work was still only a theory, it inspired a young German physicist called Heinrich Hertz. Hertz decided to dedicate himself to designing an experiment to prove that Maxwell's waves really existed. And here it is. This is Hertz's original apparatus, and its beauty is in its sheer simplicity. He generates an alternating current that runs along these metal rods with a spark that jumps across the gap between these two spheres. Now, if Maxwell was right, then this alternating current should generate an invisible electromagnetic wave that spreads out into the surroundings. If you place a wire in the path of that wave, then at the wire there should be a changing electromagnetic field which should induce an electric current in the wire. So what Hertz did was build this ring of wire, his receiver, that he could carry around in different positions in the room to see if he could detect the presence of the wave. And the way he did that was leave a very tiny gap in the wire across which a spark would jump if a current runs through the ring. Now, because the current is so weak, that spark is very, very faint. And Hertz spent pretty much most of 1887 in a darkened room staring intensely through a lens to see if he could detect the presence of this faint spark. But Hertz wasn't alone in trying to create Maxwell's waves. Back in England, a young physics professor called Oliver Lodge had been fascinated by the topic for years, but hadn't had the time to design any experiments to try to discover them. Then, one day in early 1888, while setting up an experiment on lightning protection, he noticed something unusual. Lodge noticed that when he set up his equipment and sent an alternating current around the wires, he could see